This is the third video in a series of 7 about hypothesis testing. One mean. Suppose we wanted to prove that the average IQ of a certain group is below 95. Let's go through the hypothesis testing 5 steps to analyze this claim. Suppose we want to test this claim with a significance of 10%. What does that mean? That means that the probability of a false positive, should it be less than 10%, we will accept the claim as proved. In other words, if we do a statistical analysis and we find that the probability of a false positive is less than 10%, we will accept that the average IQ is below 95. So we sample our data, and let's say that we test 36 people. The group average is 91.3. Also, we're going to assume in this case that we have an estimate of the population standard deviation, so suppose that that's 15. Now here's something to ponder. We're trying to prove that a group average, a population average is below 95. And when we sample 36 people, they get a 91.3 IQ average. That seems significantly below 95. But the question we always have to ask ourselves is, was that lower than 95 because the average IQ actually is below 95, or was it lower than 95 just by chance, just by random sampling? And that's what our 5-step process is going to reveal. Notice we have a group average of 91.3, and that's below the claim of 95 by 3.7 points. 95 minus 91.3. Now, as far as the 5 steps go, the first 2, assuming you're a student in a statistics class, the first 2 will always be done for you. The claim will be made, the significance will be stated, and the so-called sample data will be printed in the problem. It's unlikely that you'll be out as a first-year statistics student doing your own research. So on to step 3, which is really our first step as a statistics student. We want to take the mindset of assuming equality. And by that, I mean, contrary to the claim that we're trying to prove, which is that the average IQ is below 95, we're going to assume, for the sake of argument, that it's exactly 95. Now, this is counter to what we're trying to prove, and we call this the null hypothesis. And we do this because if we can do a calculation based on this assumption, on this hypothesis, and that calculation reveals that our sample data are a rare event, then that will cast some doubt on the assumption, and we'll be able to reject the null hypothesis and assume that the alternate hypothesis, the thing we were trying to prove in the first place, is likely to be true. So in terms of assuming equality, what if the population average were exactly 95? Let's look at our sampling distribution and see what that would look like. If we look at a sampling distribution of sample averages, and when I put x bar here, I don't mean the x bar that's 91.3 specifically. I'm thinking more generally about what if we were to sample 36 people over and over and over and over and chart all of our sample averages. Then most of them would cluster around 95 if the null hypothesis were in fact true. And there would be some that would vary left or right of that. But this bell curve, this sampling distribution, represents the scattering of sample averages that we would get if we were to do this process over and over. Now, the question we have to ask ourselves is this particular sample average of 91.3, is it just a little bit lower than 95, in which case it wouldn't be statistically significant, or is it much lower than 95 in this acceptance region, where we could say that's so much lower than 95, it's so unlikely to have happened by chance that we're willing to reject the red statement or reject the null hypothesis and accept the green statement known as the alternative hypothesis. So, in order to answer that, we'll move on to step 4, which is really our second step, and we'll find the probability that our sample could be that low. Now, when you're testing claims about a mean, you have a formula for standard error. You may be familiar with this if you've already studied confidence intervals. If not, there's the formula. We have a test statistic, which is essentially just the number of standard errors our sample is from the mean. And we're going to use our normal distribution to compute the probability that the sample could be this low. So here goes the actual calculations. I'm going to take my population standard deviation and divide it by the square root of sample size. So my standard error works out to be 2.5. Now the question is, the 91.3 sample average that I got from those 36 people, how many standard errors is that away from the mean of this sampling distribution? Well, we were 3.7 points below the mean, and if you divide that by 2.5, the standard error, you'll get the number of standard errors, which in this case is 1.48. And if I then compute the normal CDF using 1.48, I will get 0.069, or about 6.9%. What does that mean? That means that if the null hypothesis were true, in other words, if the population average were exactly 95, there is about a 6.9% chance that I could get a sample of 36 people to have this low of an average. And now on to stating our conclusion. Recall that we set out to test this claim at a 10% significance. In other words, the probability of a false positive being anywhere up to 10% would have been acceptable for us to accept that the average IQ is below 95. Well, 6.9% is lower than 10%, and therefore there is sufficient evidence to support the claim that the group average is below 95. Are we 100% sure of that? No, you can never be 100% sure, but we've concluded that there's only a 6.9% chance essentially that we're wrong, and we're taking that as evidence, in this case, that we were right. Hence, the claim is proved. Let's look at another example. Suppose we wanted to prove that the average retirement age for members of the military is over 40. And suppose we wanted to test this claim with a significance of 1%. That means if there's a less than 1% chance of a false positive or a type 1 error, we're going to accept the claim as stated. So here's our sample data. We surveyed 12 people. The average retirement age in that particular group, the sample average, was 44. But this time, unlike the last problem, let's assume that we don't know anything about the population standard deviation for military retirees. But we do know from our sample of 12 individuals that the sample standard deviation was 6. Now notice our sample average of 44 is higher than the claim. If we want to prove that something is over 40, and we get an average of 44, is that enough to prove it? Maybe, but that would depend. Did we get a sample average of 44 because the actual retirement age is over 44? Or did we get a sample average of 44 for another reason? Maybe it's just sampling error. And the purpose of this problem is to determine which of those two scenarios is the case. You'll notice that 44 is 4 years older than the number in the claim. The question now is that 4 years going to be enough? So we'll go on to step 3, which is our first step, and we're going to again assume this mindset of equality. We're going to assume that the population average is exactly 40. Do we know that to be the case? No. We're assuming it for the sake of argument. We're going to build an argument based on that assumption, and if that assumption leads us to an unlikely event, we're going to reject our assumption and accept the alternative hypothesis. That's why we do that. To do that, let's look at a sampling distribution of sample averages. Now again, when I put an X bar here, I'm not talking about our specific sample average of 44 from our data. I'm looking at a sampling distribution that shows what would happen if we repeatedly took samples of 12 people from a population whose average was exactly 40. And most of those samples would be around 40, and of course some would be higher and some would be lower, and that's the meaning of this, what we'll see to be called our t distribution, which is very much like the normal distribution. So the question is the 44 just slightly above 40, or is it significantly above 40 to where we'll be able to accept that the average retirement age is over 40? So to do that, here comes the bulk of the calculation. We have to compute the probability that our sample could be as high as it was, assuming that the population average actually is 40. Since our claim is regarding a mean, we're going to have our standard error formula. Notice, by contrast to the previous problem, here we're using the sample standard deviation because we don't know the population standard deviation. Accordingly, our test statistic, which is the number of standard errors, is going to be a t-value rather than a z-value, and we're going to use the t-distribution to solve this problem. That's what we always do when we don't know the population standard deviation and we're just using the sample standard deviation as a substitute. And likewise, on our graphing calculators or other software, where you're going to use the t cumulative distribution function to find the probability of the sample being as high as it is. So here go the actual calculations. I plugged in my sample standard deviation, my sample size. I got my standard error of 1.732. I want to know how many standard errors my sample average is from the mean. Well, we know that our sample average is 4 higher than 40, so how many standard errors is that? Well, I'll have to divide 4 by the standard error to find that out, which gives me a t-score of about 2.3. I can then plug that in to the t-CDF function, and notice the degrees of freedom is 11. You may have learned in other problems or courses that the degrees of freedom is always 1 less than the sample size. In this case, our sample size was 12, so our degrees of freedom is 11. Calculator figures out that the probability is approximately 2%. So what does that mean? That means if the null hypothesis were true, if the population average were exactly 40, there would be a 2.1% chance that our sample could be this high. Now that's not very likely, and in some sense that gives strong evidence to support the claim. In the previous problem, we had a p-value around 6%, and that was enough to support the claim in that case. However, in this case, we decided, in terms of our conclusion, that we would only accept probabilities of false positives as high as 1%. That was stated outright in the beginning. And the probability of that kind of error here is 2%. And as low as that is, it's not lower than 1%. And accordingly, my final conclusion is that because 2% is higher than 1%, there is not sufficient evidence to support the claim that the average retirement age is over 40. There is evidence leaning that way, certainly, but not to the high standard that we set at the beginning of the problem. And that concludes part 3 of 7.